All right. The last couple days we've been working with the measures of angles. We talked about the measures of angles. We talked about reference angles. We worked with radians. We've talked about degrees, minutes, seconds. Had a worksheet that involved mainly the radians and the degree, minutes, seconds. Today's Is there any questions that you have on anything in regards to radians, working with the radians? If we take a look at problem number 6, or number 12, I'm sorry, 6 radians. Six radians is equal to how many approximately number of degrees? Now, what we had before is we had things that were 17 pi over 18. Well, when we had the value of pi in there, we could take 180 and substitute it in for pi. So we can do 17 times 180 divided by 18. Or we can take 180 divided by 18, which is 10, times 170 by 17, and you get 170 degrees. What I have in problem number 12 is we have just 6 radians. We have no pi's in there. Okay, so there's no 180s that we can substitute in for pi. So when that happens, we have to go back to the ratio pi over 180 is equal to x number of radians over theta number of degrees. The number of radians we have is a value of 6. So we have pi over 180 is equal to 6 over theta. This gives us a proportion that we have to solve. We diagonally multiply and we divide. Well, we diagonally multiply. We have theta pi is equal to 180 times 6, but we want to solve for theta here. So solving for theta, we have to divide both sides by pi. Now that value of pi is 3.14. So we have 180 times 6, but we have to divide that bit by 4. So we have 1040 or divided by pi. And that will give you an approximate number of degrees, which is 343.8 degrees. Okay, when you don't have the pi in there and you're doing the conversions, and you can just hit your pi button on your calculator, when you don't have the pi in there and you're trying to do the conversions in there, you have to use the proportion to be able to solve. Other questions you have? Today's worksheet will deal with some reference angles also, so you can go through some of the ideas with reference angles. As you keep up with the material here, it will catch up on you real quick. Because the things that we do in trig class, actual trig class, we're doing all over again, but we're going to be doing it at a little bit quicker pace. Because there's some things that we did not go through in trig class that we have to add into the actual class here. And today is one of those. Today we're going to talk about angular speed. We're going to talk about areas of sectors, arc lengths. When we talk about the arc length of a circle, Arc length on a unit circle. Once again, the arc length on a unit circle is your number of radians. Your arc length on a unit circle is your number of radians for a degree measure of a central angle. Arc length and radians are synonymous with each other. They are synonymous with each other. So when you're talking about the arc length, you're talking about the radians. Well, if we have an angle of 60 degrees, what is the arc length for that angle of 60 degrees? Well, if I'm asking you what the arc length is, that's also your number of radians on a unit circle. So if we take a look on a unit circle, the arc length or your number of radians on a unit circle of 60 degrees, what's your number of radians that you have in terms of pi? 60 degrees, Grand Shannon, what do we have? What's your number of radians? Pi over 3. Okay, so what we have here is the arc length, which is your number of radians, is pi over 3. They are the same thing. If I take a look at 60 degrees, if we have 60 degrees there, this arc length on the circle is pi over 3, which is also the number of radians. Well, what happens if the radius gets increased to 4? What's the arc length of a 60-degree angle? What is the measure of that arc length going to be? If it's a unit circle where the radius is 1, the arc length is going to be the pi over 6. That's what's nice about the unit circle. What's going to be the arc length when the radius increases to 4? Well, let's go back to what we had to begin with. We talked about the circumference was 2 pi. The circumference on the unit circle over here was 2 pi. If we take a look at 60 degrees, what part of the circle is 60 degrees? What part of the circle is 60 degrees? What fractional part would that be of the entire circle? Jack? 1/6. 1/6 because the entire circle is 360 degrees. Well, 60 degrees of that is 1/6. So if I take this 2 pi and multiply by 1/6, this is another way of coming up with this pi over 3. What is our circumference over here? If my radius is 4, what is our circumference now? Kylie, what's our circumference now? My radius is 4. When my radius was 1, my circumference was 2 pi, because how I calculate the circumference is 2 pi r. Now my radius is 4. So what's our circumference going to be now in terms of pi? 8 pi. So our circumference over here is 8 pi, or 4 times 2 pi. 4 times 2 pi. But I'm still dealing with 60 degrees. And 60 degrees, as Jack told us, was 1/6 of the circle. So what we have now is, rather than 1/6 of just 2 pi, we have 1/6 of 8 pi. So we could take this 1/6 and multiply it by this 8 pi. What are you looking for? Nope. So we have 8 pi over 6, which reduces down to 4 pi over 3. But the thing we want to take a look at also is to dig a little bit deeper in this. Here we have our pi over 3, which is the same as this pi over 3 over here. Here we have the value of 4, which is our radius. So when dealing with the arc length, how we can calculate our arc length is we could take our radius and multiply it by theta. They use theta in the book. That's why I put theta down there. I don't like using theta when dealing with radians. I like using the x a little bit more when dealing with radians. But if we take our radius and multiply it by our arc length in radians, our radian measures of the degree measure, I can also come up with your arc length. Like I said, what I like is I like Rx a little bit better, because x is your number of radians. So when dealing with the arc length, we're trying to find the measure of an arc length here. We're trying to find the measure of an arc length. We could multiply by whatever fractional part we have to the entire circumference, or we could take the number of radians we have in our degree measure and multiply it by the radius. When dealing with a sector, and like I said, these are two things that this whole section that we're going through today, we didn't go through in trig class. Okay, so this is not a trig. It's not a trig, actual trig class type of thing. This is something that's additional to what we do in trig. A sector is a region in the interior of the circle bounded by 2 radii. It's a region in the interior of a circle bounded by 2 radii. Now, when you're talking about the arc length is just the pizza crust. It's the outer edge of the pizza crust. The sector is what we like. The sector is the good stuff. It's the sauce, it's the cheese, it's the actual pizza. It's the actual pizza. So when you're talking about a sector, that's all this right here. This is the sector. We have two radii. What's in the interior of that radii? Okay, that is called a sector. We have a radius of 6 feet. We want to find the area of the sector bounded by 120 degrees. Once again, there's different ways of dealing with this. I like dealing with a little bit more like we did the initial one up top. I don't like memorizing an additional formula there. I like to use my noggin a little bit more. If I have 120 degrees, what fractional part of a triangle is 120 degrees? 1/3. That's 1/3 of the triangle. Well, what we're looking at here is we're looking at area. Now we have to go back and remember, how do I calculate the area of a circle? Oh boy. Area of a circle, how do we calculate the area of a circle? Circumference is 2 pi r or pi times diameter, one of the two, it doesn't matter. How do I find the area of the circle? Pi r squared, that's correct. So if I took a look at the entire area of this circle, my radius is 6 feet. The radius is 6 feet. So in terms of pi, I have pi times 6 squared, pi r squared, or 36 pi. That's the area of the entire circle. What Grace said up here is 120 degrees is 1/3 of the entire circle. So what we're going to want to take is 1/3 of the entire area. So the area of the sector is 1/3 times 36 pi. Which is 12 pi squares. If you leave it in terms of pi, that is fine. If you are that type of person, if you're that person that I need to have an exact number, I can't use pi there, and you want to multiply by 3.1415718281828, if you want to do that, that is fine. If you want to hit your little pi button on your calculator, that is fine. But if you leave it in terms of 12 pi, that is also fine. It's 37 and some change, so. Area of a sector. We take the area of the circle and we multiply by the fractional part of the circle. How do we calculate a fractional part? You take the number of degrees divided by 360. Or if we wanted to, we could take the number of radian measured divided by 2 pi. If you're bent on formulas, do you like the formula idea? You can also calculate the area of the sector. 1/2 radius squared times your number of radians. I like fractional part times the circumference or the area of the circle. Reason why is there's hopefully some comfortability that you have in calculating the area of a circle and circumference of a circle. Because you've done it since probably 5th or 6th grade. You calculate the area and circumference of the circle. So you calculated circumference by 2 pi r or pi times diameter, or calculate the area by pi r squared. and you know how to calculate that. This just adds another formula into it. If you can remember how to find the circumference, if you can remember how to find the circumference of a circle or an area of a circle multiplied by the fractional part's a lot easier to deal with. I have 100. If I had 30 degrees, one part of the circle is 30 degrees. Well, 30 is divided by 360 is, cancel out the zeros. You have 1/12 of the circle. If I have 180 degrees, that's half the circle. So I multiply by a half. Find the area of the sectors for a circle with a radius of 5 feet for a degree measure of a central angle of 240 degrees. What we're going to do is we're going to find both. We're going to find the arc length. We're going to find the area of the circle and also the arc length. Well, if we have our theta is 240 degrees. What is the fractional part of that? 240 degrees. I got a circle, it's 240 degrees. I've rotated 240 degrees. I want to find the arc length and then whatever is in the interior here, the area of the sector inside there. Well, 240 degrees is what part of a circle? Justin? 2/3. We have 240 divided by 360. Okay, we get a value of 2/3. The area of the circle and the circumference of the circle. Area of the circle is pi r squared. Circumference is 2 pi r. My radius is 5 feet. Find your circumference in terms of pi and the area in terms of pi. Sophia, what's the area? The total area of the circle. 25 pi. Taking pi r squared, the circumference of the circle is going to be what, Jana? 10 pi. So to find the area of the sector, I can take our fractional part, 2/3 of 25 pi. To find the arc length, we can take 2/3 times our 10 pi. And once again, if you want to leave it in terms of pi, that is fine. Just make sure your fractions are reduced. So we have 50 pi over 3 here, and the arc length would be 20 pi over 3. Now, if we go into the formulas, 240 degrees. 240 degrees, what would that be in terms of radians? (240 degrees is how many radians in terms of pi? run it through the proportion, or you can also think about our three main values. Pi over 3 is 60, pi over 4 is 45, pi over 6 is 30. What can I do with one of those values to get to 240 degrees? Well, you can run it through the proportion and the conversion. Cole, what's our number of radians in terms of pi?
4.2.
In terms of pi?
In terms of pi.
Isaac, what's in terms of pi?
2 pi.
2 pi over 3. Yeah.
Is it 4 pi over 3?
4 pi over 3. Okay, if I take a look at this, I have 60 degrees. What do I multiply 60 by to get 240? I multiply 60 times 4. 60 times 4 is 240. 6 times 4 is 24. Add your 0. Okay, so whatever I multiply by here, I multiply this by 4. I multiply that by 4. 4 pi over 3. Or if I go pi over 180 is equal to x over 240. I have 240 over 180. I can put it into my calculator. 240 divided by 180. Hit your math button. Hit enter. You get 4/3. So my number of radians is 4 pi over 3. So if I take a look at my arc length, if I multiply this by my radius for my arc length, I can take the 4 pi over 3 and multiply by my radius of 5. So I got 5 times 4, which is 20 pi over 3. The other one is 1/2 times your radius squared times your number of radians, which is 4 pi over 3. So we have 25. We have 25 here times 100. There times 4, that gives me 100 over 6. Which I could take 2 out of top and bottom and give me back to my 5 pi, 50 pi over 3. Once again, I tend to opt into this a little bit more because this requires me to remember another formula. The first one's not bad. You take your radius times your arc length in radians. That's not bad. But the second one, you have to work a little bit harder for. Linear velocity, average velocity, how do we calculate that? How fast you go, what's your total distance, how long did it take to go that far? If I run the 100-meter dash in 10 seconds, we have 100 divided by 10, which is 10 meters per second. Your average velocity is 10 meters per second. That's your actual velocity instantaneous, but because you start at 0, you have to accelerate past that to be able to get your average velocity at 10 meters per second. So what we talk about with respect to linear velocity, your average velocity is whatever your total distance is divided by your amount of time. Well, when I talk about an arc length, your arc length is calculated times your radius times x. Radius times x, that's our arc length. Your fractional part times x. When we talk about an arc length, your distance is an arc length. When you talk about an arc length, that's a distance. If I would be able to take a pair of scissors and cut the circle and straighten out to a straight line, I can find a length to that. So when you talk about a linear velocity or average velocity, it's your total distance divided by time. This turns into your arc length divided by time. Because my distance I'm dealing with is my arc length. So we have S divided by T. This goes into our angular speed now. Angular speed is your amount of radians that you're traveling per unit time. Okay, you have two speeds here. You have a linear velocity or linear speed, and you have an angular speed. It's basically asking how many degrees am I going through in an amount of time. That's your amount of angular speed, your RPMs. So we have arc length is radius times your angles. So we have this number of radians you have. If I divide both sides by my value of R, divide by R, we have your number of radians, your angular radians is equal to your arc length divided by your radius. So when you talk about a linear velocity, of something that is spinning around, if you had a weight on a string, you had a weight on the string that you're spinning around, you have two different velocities there. You have an angular velocity and you have a linear velocity. Your linear velocity is going to be an instantaneous velocity. And this is something to get into when you get into calculus and physics. It's a tangential velocity, it's an instantaneous velocity. Your linear velocity can be calculated by your radius times your angular velocity. And once again, this is omega. It is like a curvy W. It's a roundy W. That's an omega. When you talk about an angular speed, you're going to be talking about radians per second or revolutions per second. Your RPMs, bless you. Your RPMs in your car. You have a speedometer, miles per second, or miles per hour dial in your car, but you have a second dial over there that measures your rotations or revolutions per minute, RPMs. To compute angular velocity, you must be in radians per unit, or radians per unit time. So when you calculate your angular velocity, this here needs to be in radians per time. Because what you'll also be given is you'll also be given revolutions per time. If you have 5 revolutions per minute, what is your number of radians per minute? Well, if I take a look at one revolution, one time around, one revolution is one time around the circle. how many radians are in one revolution? How many radians are in one revolution? 2 pi. If you have one revolution, that is equal to 2 pi radians. So to convert 5 revolutions per minute to radians per minute, every revolution is 2 pi radians. So how many radians per minute is 5 revolutions per minute? 10 pi. Because each one of these revolutions, you're spinning around an entire circle. If I start here and I go one time around, this is one revolution. How many radians is this now? Well, that's one time around. That's still 360 degrees, which is 2 pi radians. So to take it from revolutions per minute into radians, you go from revolutions to radians, you just multiply by 2 pi. How many revolutions do you have? If the weight at the end of a 4-foot string is being twirled at a rate of 50 revolutions per minute. Okay, I got a string, I got a weight on it. I'm just spinning around. I have a string here, and I'm just spinning this weight around. Okay? Spinning around. What is the linear and angular velocity of this? Well, the radius is 4 feet. So you have this weight that's being spun around at 50 revolutions per minute, RPMs. What is the angular velocity and linear velocity? Well, our angular velocity is 50 revolutions per minute. That's an angular velocity. You're spinning it around. But to put this in terms of pi and radians, which is more useful, how many radians per minute is this going to be? Austin? 100 pi? Hundred pi radians per minute. That is your angular velocity. To calculate your linear velocity, we could just take our angular velocity and multiply it by its radius. So our linear velocity is r times omega. My radius is 4 feet. So we have 4 feet times 100 pi, or 400 pi feet per minute. And this is your linear velocity. Once again, all this material is something that we did not cover in trig class. So it's a little bit newer to you. You guys are all smart cookies. Okay, the worksheet I am giving you is sort of a combination of what we've done the last couple of days. Got some reference angle ideas for you there. Got some reference angles, got some radians, got conversions in there. Then we go down to dealing with some of the arc lengths and some angular velocities, some reference angles at the bottom, and some areas of sectors on the back, some revolutions per minute, and angular velocity on the back also. Questions? All right, rest of the time is yours.